Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at statistical independence and some averages of functions of joint random variables. This will actually be a second look at statistical independence, and to begin we'll do a little review and look at some notation and some concepts that we first talked about back when we were discussing basic probability theory and set notation. So here goes. Statistical independence. Statistical independence. Statistical independence yields the following result. Probability of events A and B occurring simultaneously, and that comma always means a conjunction, and the probability of A and B occurring simultaneously, also written as the probability of A intersecting B, equals the product of individual probabilities, probability of A times the probability of B, if A and B are statistically independent. All right, that's our central result. The probability of A and B occurring simultaneously equals the product of individual probabilities if A and B are statistically independent. Let me point out another result from that earlier discussion. If this is my universal set or sample space S, and that's event A and this is event B, there's my intersection, A intersect B. Another result we found a long time ago, assuming A and B are neither the empty set, so we'll begin by assuming that neither A nor B are the empty set. Then A and B cannot be both mutually exclusive and statistically independent. So, and you'll recall that being mutually exclusive implies that A intersect B equals the empty set, or probability of A intersect B equals probability of A and B occurring simultaneously equals 0. So these two pieces at the bottom of the board are what are meant by being mutually exclusive. All right, so events A and B cannot be both mutually exclusive and statistically independent, assuming that both A and B are not the empty set. More importantly, is the result at the top of the page here. The probability of A and B occurring simultaneously is the product of individual probabilities. All right, let's extend this to joint random variables. And we'll assume that I have two random variables, x and y. I'm going to assume that x and y are statistically independent. All right, now I'm going to define two events. I'm going to let event A equal x less than some value little x, and B equal the event that random variable y is less than or equal to some level little y. All right. Well then, the probability that x is less than little x and capital Y is less than little y equals my joint cumulative distribution function. And because, let's write this down here. This is event A and this is event B. Since my random variables x and y are statistically independent, then events A and B are going to be statistically independent. And I can write my joint cumulative distribution function as the product of probabilities. And that is simply the product of marginal cumulative distribution functions. All right? So if x and y are statistically independent, my joint cumulative distribution function can be written as a product of marginal cumulative distribution functions. It's kind of an important result. All right? Moreover, remember this, my joint probability density function, which is the partial derivative with respect to x and partial derivative with respect to y of my joint cumulative distribution function. That is simply going to be the product of marginal PDFs. All right? If I take this result, the product of marginal cumulative distribution functions, put it into there, then I just get the partial derivative with respect to x of the cumulative distribution function as a function of x times the first partial derivative with respect to y of my cumulative distribution function as a function of y. So if x and y are statistically independent, I get that my joint PDF equals the product of marginal PDFs, and that is also another important result for today. Okay? Let's also extend this to conditional PDFs. We're still assuming that my random variables x and y are independent. All right, and let's write this down. That is a conditional probability density function. It's the probability density function of x, random variable x conditioned on y. We saw earlier that this is my joint PDF divided by my marginal PDF for y. And from the previous slide, my joint probability density function is just the product of marginal probability density functions. Oh, I did it again. And those guys cancel out, leaving me just a marginal probability density function for x. So if x and y are statistically independent, that means x doesn't depend upon y. So the probability density function of x conditioned on y just equals the probability density function for x. That should go without saying. And by extension, the probability density function for y conditioned on x will just be the marginal probability density function for y. All right. If x and y are statistically independent, meaning they don't depend on one another at all, then the conditional probability density functions are equal to the marginal probability density functions for each random variable in isolation. All right, that's all I want to say about statistical independence for the time being. We'll use this concept in some examples and some problems a little bit later on. Now, let's talk about some averages of functions of two random variables. Averages of functions of two random variables. All right. I'm going to let x and y be two random variables. They may or may not be statistically independent. For the time being, let's assume that they are not. These are my two random variables. All right. Remember, a random variable is a function. It's a function that assigns a real number to an event. Z is going to be a function of x and y. G is some function. A function of a function is a function. A function of two functions is a function. So if x and y are both random variables, a function of those two random variables is a new random variable. All right? All right. We're not going to talk a whole lot about z itself. We're going to really interest ourselves with the function g. So recall this from a long time ago. Recall that the expected value of a function of a single random variable equaled the integral over all possible values of g of x times the probability density function for x. All right? By extension, we have the following. The expected value of a function of two random variables is just going to be a double integral g x y times my joint PDF. All right? By extension. This is true if x and y are continuous random variables. That's if they're continuous random variables. I can also write this down for discrete random variables. I probably need to make that look like a random variable there. If x and y are discrete random variables, then my integrals become summations. This is if x and y are discrete. Okay? That's how that looks. So that's how you find the average or the mean value of a function of joint random variables. The relationship that we will use more often than not for our work this semester is that one right there. All right? Let's look at a special case. A couple of special cases, actually. what if x and y are statistically independent and G is separable? All right, so this is a special case. It's actually an interesting special case that we're going to come back to a couple of times. But we'll assume that x and y are statistically independent random variables and G is separable. Well then, the expected value of the function is just my double integral of g x x g y of y times, remember, if my random variables x and y are statistically independent, then the joint probability density function is just the product of marginal PDFs. And then I can separate out my integrals into one variable integrals. Integral from minus infinity to plus infinity g of x times f of x times the integral of g of y times PDF for y. And then this is simply the expected value of g sub x times the expected value of g sub y. All right? So this is a special case, but it's kind of an interesting special case that we will come back to from time to time today. All right? Let's now discuss linearity. All right. In particular, if g of xy is a linear summation of other functions of xy, if g is the linear summation of two other functions of xy, then the expected value equals so if g is a linear summation of g1 and g2, then the expected value of g is the linear summation of the expected values of g1 and g2 independently. That should be almost obvious. If it's not, let me know. We'll talk about it some more. All right, let's do some examples. Let's let my joint PDF be something like this. Alpha, beta over 4 let's let that be my probability density function. That's not one we've actually looked at before, but it's a proper probability density function. Has a volume of 1. It's always positive. You'll notice that this is separable. I can write this as alpha over 2 e to the negative alpha absolute value of x times beta over 2 e to the minus beta times absolute value of y. Because my PDF is separable, that means that x and y are statistically independent. Okay, and this is just the product of marginal PDFs. All right, that's what that looks like. If we sketched one of these, it would look something like this. Let's just assume that that's x, and this is the marginal PDF for x. It's going to look something like that. It's going to exponentially decay about the origin, and this peak value here will be alpha over 2. And this area will be 1. The total area under that curve will be 1. All right, the proper probability density function. All right, well, let's find a few things. I'm going to let's write that a little bit nicer. Not sure if I did. So my function now is just going to be the product of x and y, and I want to find the mean. Find the mean of g. That's that. All right. And because my function is separable and my random variables are statistically independent, I get the following. That's an absolute value sign. Times beta over 2 all right, I can break it down that way. Now what I'm going to do is I want to point out to you that my marginal probability density functions are even. That's an even function. This is also an even function. X and y alone are odd functions. Those are odd functions. X and y are odd functions. Anytime I integrate the product of an odd and an even function in a symmetric interval around the origin, in this case from minus infinity to plus infinity, that's certainly symmetric about the origin. Anytime I integrate the product of an odd function times an even function over a symmetric interval around the origin, I get exactly 0. So both of these integrals are 0, and therefore the product of the integrals is 0. Exactly. Don't have to do any more work. That's an interesting thing to look for. We've looked at even and odd functions a couple of videos back. Make sure you look for them. It'll help you simplify your results in some cases. Let's continue this example, part B. Let's let g of x, y equal something different, not separable. X squared plus y squared. This is not separable. Okay? And I want to find the mean of g. So the expected value of g is my double integral of my function x squared plus y squared times my joint PDF alpha beta over 4 e to the minus alpha absolute value of x plus beta absolute value of y dx dy. And then I can simplify this as follows. I get the integral from minus infinity to plus infinity x squared alpha over 2 e to the minus alpha absolute value of x dx times integral from minus infinity to infinity of beta over, let's make that a little bit better, beta over 2 e to the minus beta absolute value of y dy plus integral from minus infinity to infinity of y squared beta over 2 e to the minus beta absolute value of y dy times the integral from minus infinity to infinity of alpha over 2 e to the minus alpha absolute value of x dx. Let me check that, make sure I got everything written down correctly. Looks like it. Okay. So, by definition, the marginal probability density functions have unit area. So, this integral is 1, and this integral is also 1. All right. And what results is the integral of minus infinity to infinity x squared e alpha over 2 e to the minus alpha absolute value of x dx plus integral from minus infinity to infinity of y squared beta over 2 e to the minus beta absolute value of y dy. Let me move to the next page to continue this. This is clearly the result. The result at the bottom of the last page was integral from minus infinity to infinity of x squared times the marginal PDF for x plus integral from minus infinity to infinity y squared times the marginal PDF for y. And this is just the mean squared value for x plus the mean squared value for y. It's the sum of the normalized powers. Sum of the mean squares, sum of normalized. All right? All right, well, let's go ahead and evaluate that. Let's find what the normalized powers actually are. We'll do it for the mean squared value of x, and by extension, we'll get the mean squared value of y by symmetry. Now what I'm going to do is I'm going to let, let's do this. I'm going to get rid of my absolute value signs by doubling my integral around the origin. That'll give me x squared e to the minus alpha x dx. Okay? Get rid of my absolute value signs by noticing that my marginal probability density function is symmetric about the origin, and so I can just double my integral. The next thing I'm going to do is I'm going to make a change of variables, and I'm going to let u equal alpha x, du equal alpha dx, and of course x squared equals u squared over alpha squared. Make my change of variables, and I get the following. 1 over alpha squared, integral from 0 to infinity of u squared e to the minus u du. And that integral I couldn't do by hand. I looked it up in one of my integral tables, and I got that. That integral, the integral from 0 to infinity of u squared e to the minus u du, happened to be a definite integral that was available in the back of one of my calculus books. All right? All right, that's that. So similarly, the normalized power for y squared would just be 2 over beta squared, and then the result for part B is okay, that's that. So for my function, when my function is the sum of x squared plus y squared, and my PDF was that double-sided declining exponential that I showed you earlier, that's the result for the expectation of x squared plus y squared. All right. As in many of these examples, it's the results themselves are not particularly interesting. It's the steps that we use to get to them that are hopefully more helpful and relevant to you. All right, let's look at some averages of some special functions. Let's look at some averages of special functions of two random variables. First one is going to be called joint moments. Joint moments. it's going to look like this. M sub mn is going to be the expected value of the product of x raised to the mth power and y raised to the nth power. So my function is x to the m, y to the n, and in all cases m and n are integers. All right, 1, 2, 3, 4, etc., etc., etc. 0 could be 0. All right. So let's look at some special ones of these. The M10 case is just the expected value of x, the mean of x. The M01 joint moment is going to be the expected value for y. All right. And there's another one. The M11 joint moment is a really very special one. This one is so special we're going to give it a name. We're going to call this one R sub x y, and it's going to be called correlation. Okay? The M11 joint moment is going to be given a special designation, a capital R sub xy, and we're going to call that correlation. We're going to explore the concept of correlation quite a bit over the next several weeks. Okay? Continuing with the notion of joint moments, let me give you a special case. If x and y are statistically independent, if x and y are statistically independent, meaning that the joint probability density function is separable, then the mnth joint moment is integral from minus infinity to infinity of x raised to the mth power times the marginal probability density function times the integral from minus infinity to infinity of y raised to the nth power times the marginal probability density function for y. And that is simply the expected value of x raised to the mth power times the expected value of y raised to the nth power. All right. Product of x raised to the nth, product of the means of each random variable in isolation raised to either the m or nth power. Let's look at correlation. If x and y are independent, then the correlation, which equals the M11 joint moment, which equals the expected value of x raised to the first power. Remember, they're statistically independent, times the expected value of y raised to the first power. That's just going to be the product of means. All right? If x and y are statistically independent, then the correlation is just the product of means. That is also a result we're going to use a little bit later on. So hang on to that for now. All right. Last major concept for the day. We want to talk about joint central moments. All right. This looks like this. Mu mn is the mnth joint central moment. That's going to be the expected value of x raised to the nth power after first subtracting off its mean times y raised to the nth power after first subtracting off its mean. All right. So in both cases here, mu x is the expected value of x in isolation, and mu sub y equals the expected value of y in isolation. All right. Expectation is always implies an integral, so it's going to look something like this. We won't calculate this integral many times. I'm going to show it to you for completeness, though. It's going to be x minus mu x raised to the nth power times y minus mu y raised to the nth power times my joint PDF. Strictly speaking, that's how you're going to calculate it, based on an integral. Expectation always implies an integral. We're not going to do that too many times. Instead, we're going to notice a few things. First of all, mu 2, 0 equals the expected value of x minus mu x squared. And that is simply the variance of x. That's what that is. It's the variance of x. All right. Similarly, made my mu backwards again. Mu 02 is expectation of y minus mu y squared, and that is the variance of y. Another one that we're going to be really interested in is mu 11. Made my mu backward again. Mu 11 is going to be the expected value of x minus mu x times y minus mu y. And this one is going to be given a special name as well. We're going to call this one capital C sub x y. And this is going to be known as the covariance of x and y. Covariance. Of x and y. All right, so in each of the three results here, you'll notice that I've got, in effect, a random variable raised to the second power here. I've got a random variable raised to the second power down here. And here I've got a product of single random variables. So I'm really taking the expected value of nominally a doubled random variable. Okay? Variance and covariance. Let's look at covariance just a little bit more. Covariance is the expected value of x minus mu x times y minus mu y. All right, let's expand that out a little bit. That's going to be expected value of the product xy minus mu x times y minus mu y times x plus mu x times mu y. All right. And this is there. And simplify a bit more. I get, let's just write down the result. You can do the algebra. This will be not a very good mu. Okay, that is the simplified way for calculating covariance. This, you'll recall, is my correlation. It's the expected value of the product of x and y. All right, and recall several videos back, we saw that the variance, for example, of x was the normalized power of x, the mean squared value of x, minus the square of the mean. All right, notice the similarity between the variance for x, similarly for the variance of y, we would have, oops, all right, for variance of x and the variance of y, we have the normalized power of x minus the square of the mean of x, or the normalized power for y minus the square of the mean of y. I more or less got a random variable to the second power here and here, and I've got a second order type random variable function there. Here I've got a mean raised to the second power, a mean raised to the second power. Here I've got means multiplied. Okay? Last thing. If x and y are statistically independent, if x and y are statistically independent, we saw a couple of slides back that the correlation is just the product of means, and therefore the covariance is 0. We'll need that a little bit later. All right? That's enough for the day. As usual, if you have any questions, please feel free to contact me at your earliest convenience, and I will answer all questions as thoroughly as I am able. Have a nice day. Bye-bye.